Today I'm joined by someone I've known for some time, Martin. Martin, would you like to introduce yourself?
Hi, Paul. Yes, my name is Martin Walsh, and currently I work as a database engineer for a global cloud-based software provider.
Okay, so I'm kind of interested in partly in day-to-day work that you do, but really what I'm interested in on behalf of people who are perhaps watching the video is resilience. And I know that in our operation, we operate in each of the three global regions. We operate two, we sometimes call them clouds or nodes, but actually they're physical data centers. And they operate real-time updates to each other. So we call it active-active, where some of our customer systems sit on one of these data centers or nodes, and some sit on another. And that gets us resilience. But to do that, we operate a number of databases, and they work in clusters. And why do we have different databases at all? What's the function of these different databases?
So you're right, absolutely right. We have many databases, and they are ordered in a set of clusters, and they replicate within the cluster and across clusters. We do it for a number of purposes, a number of reasons. They can perform different roles, different functions within that cluster. They also allow us to spread load or scale in case of any sort of increase in load. We also we do it for maintenance. It means that we can isolate certain individual instances without affecting service at any time, perform any maintenance tasks and put them back into service. By pulling two or more clusters together, it allows us to perform resilience at a much higher level, where we can move customers across the globe ultimately. And so in the event of any cloud-based service provider problems, we have a higher level of resilience there, not just within the cluster, but across clusters, and therefore across continents ultimately. So
okay, so something else I understand is that when you have software that's both reading and writing to databases, and sometimes I guess end customers will end up running a report, for example, and it could be a big report that's running across all their data. Those reads effectively could take a long time, and we don't want those to slow up fast reads or writes to the database. So do we organize our databases like that? So we have kind of fast reads and slow reads and writes operating in separate machines effectively?
We absolutely do, yes. So within those clusters, I mentioned about different functions. I didn't really enlarge on that. So as you've said, we have the fast reads, or what we call the most efficient and performant reads, which are following things in the millisecond. So when an application talks to a database, it may write and it wants to read that back. These things need to happen in a very short space of time. So you want that to be the most performant. And as you say, there are other functions, namely reporting functions, which address large sets of data and can take a long time to respond. And you isolate those off into different clusters so that they don't impact each other, so to speak. And each part of the service runs autonomously and ultimately provides the service to the customers that we need.
Mm-hmm. Okay, so thinking about replication now, and you mentioned replication between databases, but I'm thinking about a customer whose primary service, if you like, is running on a data center, and there's this other data center that we could move them to. So I guess when the customer changes his configuration, updates a user profile, or just logs the fact that something action has taken place, how do we get that write effectively to the other data center? And I guess that's replication, right?
It is, yeah. There are many products out there, and depending on the technology, the database technology you're using will ultimately decide some of that. But ultimately, every database, to provide a consistent and resilient data store, will write any writes to the database are logged, and technically they're called redo logs or others, depending again on the technology you're using. And those are, for want of a better word, replicated. They are ultimately moved to where you need to replicate the data and replayed. That actually happens in near real time. We're talking milliseconds, even when it's across continents, so to speak.
Wow. Okay.
There are different methods of replication, but ultimately that's the most common.
So effectively, if one of these huge data centers, which itself has an enormous amount of resilience, was to actually go down, then the customer's data that's sitting on the other data center is pretty much there within a few milliseconds of the state that it was in before. I guess the other thing, one of the other reasons for running lots of different, perhaps identical databases, as in they're carrying out identical operations, is if a database itself slows down or fails. And by that, I mean one of those many database instances, either it drops out or you can just take it out of service and it doesn't affect anything. And I know to achieve that, we use a mechanism, which I loved when I heard about this, called a heartbeat. And I'm familiar with what obviously a biological heartbeat is. Yeah. But what is it that we do then to make use of this heartbeat capability to determine if a database is going slow or just needs to be taken, is that the right word, out of balance?
Yes, for our conversation, yes. So you're right, the heartbeat mechanism is quite common. People use it in different ways or administer it in different ways. But for us, what we do, the heartbeat, which, as you say, biologically, it's a beat, in reality is a date timestamp. And so we're injecting or writing a date timestamp to the database. Mm-hmm. And then replication, as we explained, will basically propagate that throughout the cluster and across to other clusters, depending on how large the platform is. And at any stage within that replication topology, so any one of the instances that makes up the database platform, we can read that heartbeat or beat back and compare it to the time now. So if that makes sense, if you can picture, we have X number of instances of databases and we inject a beat in one of them, it replicates throughout the number of instances, and each of those instances, we will read back that beat every second and say, the time is now, compare it to the beat or the timestamp that's in the beat, and that will give us, the difference will be the lag or the replication delay. And as I said, typically in our world, that's single digit milliseconds, basically.
Yeah, and then I imagine you're not looking at that all the time. That will be a little onerous. So there's obviously some software monitoring that, and then what, automatically shutting down a database or spinning up another if it's under too much load.
Yeah, so you're right. I don't wish to watch that all the time. We do have some pretty graphs, and it's on our knock board and things like that. But ultimately, with every one of those instances that we pictured, we'll write that comparison every second, 24/7, 365 days a year. We'll write it to a time series database, part of our monitoring infrastructure. And there are alerts based on that. We have a threshold of single digit seconds. So if any one of those instances measures a few seconds delay, that will raise an alert, and that will ultimately inform or notify an engineer. And an engineer will investigate.
Okay, Martin, it's been fascinating talking to you. We can go on and on, I think, in this subject, because replication and resilience are really important, but we're out of time. So, Martin, thank you so much for answering some questions today.
Thank you, Paul.